Good afternoon, everyone. It's really great to see so many people logged into this webinar. And over the next 35, 40 minutes, I'm going to give you a bit of an overview of what I think is a really fascinating subject, and that is the rheology of bitumen. And it kind of explains why bitumen behaves in the way it does and why the materials that are prepared from bitumen behave in the way that they do. We're going to keep it at a reasonably high level, purely because to go into real depth on the rheology of bitumen and bituminous materials, that would take quite some time. So we're going to keep it kind of high level, and we'll look at some terminology, some experiments. We'll look at some different types of bituminous behavior. And so at the end, what I hope you'll get is just a little snapshot into the way that rheology of bitumen helps us understand it, and helps us understand all of the properties that it has and how it behaves as a material and in a different product. Now, the first thing that I have to do is really start with an apology or an explanation, or a request, really. And that is, don't be afraid of the terminology. It's one of the things that is associated with any branch of science or engineering or whatever, is that we have an awful lot of terminology around, and it can be very, very off-putting when you first start talking about any of those branches of science, that you can quite quickly go into in-depth terminology, and that's not what we're going to do today. So don't be worried that I'm going to talk about things like thixotropic behavior and Herschel-Bulkley fluids and shear thinning and dilatant behavior, because I'm not going to do that. I do have to keep in mind there are some items of terminology that I can't avoid using, because otherwise this webinar wouldn't be of use. So, but I'm going to try and keep the terminology at a reasonably standard level. So we're not going to go into all the depth, and I'm certainly not going to try and define all of the words that you see on the slide in front of you right now. The second thing I want you to take on board is the fact that rheology is not just about bitumen. It's about almost everything that we come into contact with on a day-by-day basis. For example, rheology of an oil or grease is very, very important to the type of oil that you would put in your car. When you're decorating and you use non-drip paint, it's rheology that defines how easy the paint is to apply, and also that the fact that it, once applied to the item that you're painting, it stays there and it doesn't run away. It's rheology that defines all of that. And then there's two quite interesting things that I want to draw your attention to. One is custard. I like it. It's one of my favorite desserts. It's very tasty to eat, but if you put it under the right conditions, you can actually run across the surface of custard. Now, please don't try this at home, but you can go and search YouTube and you can see people that run across the surface of custard. And the reason that you can do that is because it has a peculiar rheological behavior under the right conditions. And another example is toothpaste. We quite often see stripy toothpaste. It's quite hard to understand how those stripes stay together and they don't mix up when you squeeze a toothpaste tube. But the reason that they don't is because the toothpaste is engineered to have a particular set of rheological properties that mean that when you squeeze the toothpaste tube out, the stripes stay exactly the same. Now, I'm not here to talk about custard and non-drip paint and honey and all those other things, but it's just to let you know that rheology is all around us, and it defines almost everything that we do. Everything that we ask of any material is really defined by its rheological behavior. So what am I here to do today is to talk about the rheology of bitumen, and it's absolutely fascinating. It's a fascinating material rheologically. One of the most interesting materials you could ever look at, but also one of the most difficult to analyze on a rheological basis. It's one of the three most difficult materials to analyze rheologically, the other two being chocolate and blood. Both very difficult to analyze. But bitumen is particularly interesting in from a rheological perspective, and I'll try and explain why a little bit later on. So I've spoken quite a lot about rheology. Well, I haven't actually defined what it is. Well, really, in its most basic terms, rheology is the study of the deformation and flow of matter. So it explains why water flows, why glass shatters under the right conditions, and from our perspective, why does bitumen, in some circumstances, why does it deform? Why does it do that? And in other circumstances, why does it crack? Well, rheology explains all of that, and we're going to come to the rheological testing in a moment. The term rheology was first coined back in the 1920s by a scientist called Eugene Bingham, and it's been used ever since to describe the deformation and the flow of matter. So how do we test it? Well, there are really two main classes of test, and they're related to behavior according to temperature or according to frequency. And we can subdivide those different classifications into high, intermediate, and low, whether that's high temperature, high frequency, low temperature, low frequency, etc. So when we're looking at rheological testing at high temperature, and by high temperature, I mean handling temperatures, the temperatures at which we would move bitumen about, whether we're pumping it around a refinery or a terminal, or we're delivering it from a truck into a storage tank, or we're mixing an asphalt in an asphalt plant, or we're preparing a roofing or a waterproofing membrane. At high temperature, the rheological studies that we look at are effectively viscosity. When we talk about high service temperature, really we're looking at how the bitumen behaves in a piece of equipment called the dynamic shear rheometer, and I'll explain that later. But at high service temperature, we can work out the engineering properties of the bitumen, the rheology of the bitumen, and see how it's going to perform at the very limits of its service temperature. At intermediate service temperature, we can also carry out tests in the dynamic shear rheometer, and they will give us the properties that we expect under normal day-to-day conditions. We can also look at low service temperature. Low, I'm really talking about sub-zero temperatures here. And we do that in a piece of equipment called the bending beam rheometer. And again, I'll explain how that works later on. But just there in that first section, that gives you a snapshot really of why rheological testing is so important for bituminous materials, because it allows us to gain a full service profile of the bitumen under almost every condition of either temperature and frequency that it will ever experience in its entire service life. And we don't get that from any of the empirical tests. We get an indication from those empirical tests like penetration and ring and ball softening point and others, but they're what we would call discrete. They're carried out at specific temperatures, and as a consequence, we don't get a full profile. And they're also very limited in terms of usefulness in terms of frequency. When we look at frequency, we're really looking to simulate the effects of traffic, for example, in an asphalt mix. What effect is traffic going to have on the bitumen in an asphalt mix in service? And we can simulate very fast moving traffic, and we can simulate very slow moving traffic using the same piece of equipment. We can look at appropriate temperatures for paving and compaction. And also when we look at our viscosity tests, we can look at pumping, and we can look at mixing. The important thing about rheological testing, which is not always true of the more basic or empirical testing, is we can actually relate the performance of the bitumen to the performance of the product, whether that's an asphalt mixture or a roofing or waterproofing membrane, actually in service. And that's why rheological testing is becoming so important, because we're effectively being asked to predict performance in service. Now, within Eurobitume, we have carried out two what we call data collection exercises, which have allowed us to correlate these rheological properties, the new rheological properties, with those empirical tests. So we have established a link between the two extremes, if you like. And that's actually very important, because we don't want to make a stepwise leap. We want to make sure that we understand the relation of these new properties, the rheological properties, with those old empirical tests. So, what types of rheological behavior are there? Well, there are two extremes, effectively. If we look at ideal materials or perfect materials, the two extremes are elastic behavior. It's very, very important that you don't confuse elastic with rubbery. It isn't. It doesn't really mean that. So elastic behavior means the material returns to its original state immediately after a strain has been applied to it. It doesn't take any time to recover. As I said, these materials don't exist in real life, but if you wanted to find a material that was almost completely elastic, then you find that in a material like quartz. So what about viscous materials? They're the opposite extreme. These materials flow up when a strain is applied, and when the strain is removed, they don't return to their original shape. They are effectively deformed. And an example of that is water or glycerol. They're almost completely viscous. Real materials, of which bitumen is one, always lie somewhere in between. And bitumen is particularly fascinating because of its viscoelastic behavior. I'm going to try a little demonstration now. This isn't bitumen, but it's a good simulation of it. Why is bitumen so fascinating? Because of its viscoelastic behavior. Well, I hope you can see this on camera. When bitumen is subjected to high frequency, it bounces. The stress, the strain is absorbed and it's reflected back. So this little sample here, which is silly putty, but it mimics the behavior of bitumen, it bounces back. But look at what happens if we apply a really low frequency stress to it. So it deforms, but then when we take the load off, it stays deformed. That's why bitumen is such an interesting material. Let's give you, so going into the science of it now. So with an elastic material, which you can see on the left-hand side of the screen, if we apply a strain and measure the stress, they're exactly in phase. There's no difference between those two materials. If you can't understand or can't quite relate to elastic behavior and the fact that stress and strain are automatically in phase, I have an example for you. From the world of football, the gentleman you see on the screen is Roy Keane, captain of Manchester United, captain of the Republic of Ireland from 1991 until 2005. Roy Keane is the perfect example of an elastic material, because if he was ever fouled on the football field, he would react immediately. He would take his revenge immediately. So Roy Keane was the perfect example of an elastic material. Let's look at our viscous material next. The strain and the stress are out of phase. They're completely out of phase. If I use the laser pen pointer, you can see here's our applied strain and here's the stress. So it takes some time before the material starts to react. And then when we take that strain off, out it comes. This might be more of a difficult example. And I did try to find more European football examples, but I couldn't. So the person you see on the screen now is an England footballer, played for Leeds United back in the 60s and early 70s, a guy called Jack Charlton. And Jack was the perfect example of a viscous material. Why? Because Jack always got even, but not in the same match. If he was fouled, Jack would make a note of it, and he would get even in the next game. So his response was completely lagging. It was completely behind phase. So Jack's behavior was completely viscous. Enough of the football analogies. Real materials behave differently. There's a lag, a difference between when we apply the stress, when we apply the strain, and then we measure the stress that it causes. There's a gap. So we apply the stress, strain rises up with it, but it's behind. Then we take the strain off, the stress reaches a peak, and then it falls away. So the difference between the strain and the stress is what we call the phase angle, or delta. That's the first bit of terminology that I'm going to introduce, and the phase angle is the difference between the applied strain and the measured stress. Let's put things into context. Are rheological tests new? Well, the short answer to that is no. They have been around for a number of years, and you can argue that the oldest of our bitumen tests, needle penetration, EN 1426, is actually a rheological test. Why? Because it measures deformation under load. That's what it does. It was first proposed in 1889 by a chap called H.C. Bowen. Within the penetration test, we can alter temperature and we can alter load. We can't alter frequency, but we can alter temperature and we can alter load. So what I'm trying to say there is, no, bitumen rheology tests are not specifically new. And as you said, as I said before, the terminology was published way back in 1920. The needle penetration is what you would call a static rheological test. Most tests are dynamic. Why are they dynamic? Because we change parameters throughout the experiment. So we subject the material to a strain. We then measure the stress, and then from that we measure our different viscous and elastic parameters. Remember that. So we're looking at how elastic the material is compared to how viscous it is under those conditions. Then we can calculate our rheological parameters, our individual properties from that. And then we either alter the temperature, alter the frequency, or we alter the strain. And then we go through that whole cycle again. So you can see it's a completely dynamic process. And again, that's what makes it so important and so useful to characterization of bituminous materials. So let's have a look at the high temperature end. Rheology and viscosity interchangeable at this point. We can measure viscosity in a dynamic fashion using either a rotating spindle viscometer according to EN 13302, or using a cone and plate viscometer according to EN 13702. And using either of those pieces of equipment, we can build up a complete profile of the handling temperatures and handling viscosities of the bitumen. Why is that important? Well, history teaches us, and there are some well-documented publications, that there are certain critical viscosities that we must achieve to ensure that mixing, in the case of an asphalt, paving and compaction, there are critical viscosities that we must meet, and those viscosities are related to temperature. So let's have a look at mixing temperature, at mixing viscosity. So on the graph you see in front of you, we have three different grades of bitumen: a hard, a medium, and a soft grade. We also have some dotted lines. The ideal mixing temperature is 200 centipoise or 0.2 Pascal seconds. So we can see that our soft bitumen achieves that at around about 150 degrees, our medium bitumen about 170, and the hard bitumen at 180. If, for example, we took our soft bitumen and we increased the mixing temperature to 180, all of a sudden we see that the viscosity is significantly lower than that 0.2 Pascal seconds, 200 centipoise. And the consequences of that are that the bitumen would then be too low in viscosity, too runny, and it would run off the aggregate. Conversely, if we take our hard bitumen and we try and reduce the mixing temperatures, we see that it will be too high in viscosity, and as a consequence, we won't be able to achieve full coating of the bitumen around the aggregate. So it's really important that we understand from a viscosity stroke rheology perspective the relationship between viscosity and temperature, because it defines everything that we do. The same applies to paving. With our soft bitumen, we hit the right paving viscosity, which is 2000 centipoise or 2 Pascal seconds at 120. Our hard paving bitumen has the same viscosity at a higher temperature, about 135. The same sort of things apply here. So if we take our hardest paving bitumen and try and pave it when the temperature is too low, then we're going to find it difficult to get through, to get it through a paving machine. Equally, if we take our soft bitumen and we try and pave it when the temperature is too high, we're lower than that ideal paving viscosity, and as a consequence, we might find that the material is too soft and too runny to compact, and it will be inconsistent all the way through. So it's really, really important that we understand those high temperature properties. And that's the first part of our rheological journey, if you like. Now I do have to come into some terminology because it's going to describe everything that I talk about over the next few minutes. But these are the only real terms that I'm going to use. The most common one in bitumen terms that we talk about is a term called G star, which is the complex shear modulus, which is the ratio of stress and strain. And we do tend to call it, sometimes we call it the complex modulus, sometimes we call it just the modulus. We shouldn't do that, but sometimes it happens. And sometimes we call it stiffness because it is reasonably related to the stiffness of the binder. But G star is the complex shear modulus, the ratio of stress and strain. Delta, the phase angle, that's the difference between stress and strain, those stress and strain curves that I showed you before, the phase angle, as it's called. And it gives you an indication of the degree of elasticity of the product, of the binder. Two other terms not in quite so common use for bitumen and bituminous binders at the moment. G prime is known as the shear storage modulus or the elastic modulus, and that's a measure of how much energy the binder can store when it's subjected to a load or a strain or whatever. G double prime, also known as the shear loss modulus or the viscous modulus, is a measure of the amount of energy that is lost. All of those properties fit together quite nicely and relate to each other on this triangle that you see here. So G, the complex modulus over here, loss modulus, storage modulus, and phase angle, they are all interrelated that way. So how do we test our rheological behavior? Well, most commonly, we use an instrument called a dynamic shear rheometer, and that there are various different models of the dynamic shear rheometer on the market, but they are characterized by having pretty similar components. Usually we have a fixed bottom plate. On top of that, we apply our bitumen sample. On top of that, there's an oscillating upper plate, and the whole thing is in a temperature controlled environment. So it has a heating and cooling system that's applied. Those are the common elements. What are the variables? Well, depending on the temperature range that we're operating at, our bitumen sample can be 1 or 2 millimeters thick. Our plates can be usually 25 millimeters in diameter or 8 millimeters in diameter, and the top and bottom plates are usually identical. Just very recently, it's become there's work being published on using a 4 millimeter plate, and that's to characterize our really very stiff, very stiff materials. So depending on the temperature range that we're operating in and the properties of the bitumen itself, we either operate 25, 8 or 4 millimeters in diameter and a sample that is 1 to 2 millimeters thick. Here you can see the dynamic shear rheometer in action. I have to say, this is before the temperature control chamber is applied to that. But I hope you can see there's our bitumen sample, beautifully applied, nothing spilling over to the top or to the bottom plate. And you should be able to see just at the very edge of that sample, there's a slight bulge of the bitumen, and that's absolutely critical that we get that, because it can have a big effect on the results. What do we test in the dynamic shear rheometer? Well, effectively, we measure complex shear modulus G star and the phase angle. Now, there's a big black box associated with dynamic shear rheometers that will calculate all the other properties out of that. But typically, this is what we measure. And then we can measure our bitumen behavior as a function of temperature, frequency, or of load. And we will typically do 2 types of tests. These are the most common. There's either what we call a temperature sweep. So we place our bitumen sample in the rheometer. We keep the frequency unique and consistent, and then we change the temperature, and we keep monitoring the complex shear modulus and the phase angle as we change the temperature. It's most common to start from high temperature and then move down to a low temperature. And that temperature sweep, its formal name, and I do have to mention this, I'm afraid, its formal name is an isochrone. The other thing that we can do is what's called a frequency sweep. And in a frequency sweep, we keep the temperature consistent, and then we change the frequency. So we move from high to low frequency. And that's called an isotherm, because the temperature is consistent. We can do an amplitude sweep, which will allow us to measure the effects of load on the bitumen. Not as common as our temperature sweeps or frequency sweeps, but they are in use occasionally. And we can relate then our properties that we obtain from the dynamic shear rheometer to some of our conventional properties. So let's have a look at a bitumen isochrone. So we're plotting our complex shear modulus against temperature. We have 4 grades there. There's a number of things that I want you to take away from this slide, really. The first is this complex modulus scale is logarithmic. So we see a quite significant change in complex shear modulus over a relatively short temperature range. So we can see complex shear modulus change of 1, 2, 3, 4, 5, almost 6 orders of magnitude as we go through that temperature range. The other thing to bear in mind, these are paving grade bitumens that I'm showing you here, but they all fall in a relatively parallel fashion. And the third thing is to show you the relationship between the different grades and their complex modulus. Our red line here is showing us that 162.20, the yellow line, has a similar stiffness as 3045, the dark blue line, has similar stiffness, sorry, at 50 degrees as our 3045, which is a very hard grade of bitumen, has at almost 80 degrees. So you can see the relationship between the two. Next, let's look at isotherms. Here, we're plotting, again, complex shear modulus against frequency. Here, both scales are logarithmic. We're plotting behavior at different temperatures. And here, you can see that as we move from low frequency to high frequency, the bitumen itself becomes stiffer. The complex shear modulus increases, regardless of the temperatures that we have on the scale. So as we go from low frequency to high frequency, the bitumen stiffness or complex shear modulus increases. But there's another factor to consider. Stiffness at 25 degrees, the yellow line, at low frequency is equivalent to the stiffness at 50 degrees at high frequency, sorry. So you can see why rheological testing is important, because it gives us a full profile of the behavior of the materials. So what else can we measure? Well, within our dynamic shear rheometer, we can measure the complex shear modulus, and then we can the storage modulus, the loss modulus, and the phase angle. We can also measure viscosity, low and what we call zero shear viscosity, but it's not particularly common to do that these days. But we can take our different parameters and then we can do some calculations. So we can take our complex shear modulus and the phase angle and relate it to what we call a rutting parameter or a permanent deformation parameter. So the complex modulus divided by the sine of the phase angle can give us a rutting parameter. We can do a similar thing by taking the complex shear modulus and the sine of the phase angle, multiply those two together, they can give us a fatigue parameter. So they can give us an indication of whether the pavement is going, whether the asphalt is going to deform or whether it's going to crack. We can also determine things like the viscoelastic transition temperature, the temperature at which bitumen moves from behaving in a predominantly viscous temperature, a predominantly viscous way to a predominantly elastic way. And then there are some sophisticated calculations that we can do. For example, a parameter called the Glover-Rowe parameter, which allows you to calculate the cracking tendency of bitumen. So in addition to the individual parameters that we measure, we can also do a lot of calculations and determine even more properties of the bitumen and discover more insights to how it's going to behave in performance. I'm going to give you an example of that now. One of our more recent tests that's been published is the multiple stress creep recovery test. This uses DSR equipment. Creep is a measure of flow under load, and creep measurements are designed to give you an evaluation of the behavior of a material under long-term loading. And so it allows us to relate accurately with, in our case, asphalt performance. And the multiple stress creep recovery test, or MSCRT, as it's commonly referred to, gives us an indication of rutting or permanent deformation behavior. What we do is we subject the binder to a load for 1 second. We then take the load off for 9 seconds, and then we repeat that. And we could do that over a number of different temperatures. And what tends to happen is we apply our load, the material flows, we take the load off, the material recovers, but it doesn't recover completely. So we have a non-recoverable part of the strain and a recoverable part of the strain. How does that look in reality? Well, it looks like this. The green line you see here is data associated with a paving grade bitumen, an unmodified bitumen. And you can see we deform it, we take the load off, it doesn't quite recover, we deform it again, we put the load back on, it still doesn't recover. And so gradually the non-recoverable part of the strain increases. And in real terms, that means we are getting to the material deforming. The blue line is the behavior that we get from a polymer modified bitumen. And here you can see the load is applied, the load is taken off, the recovery is much more complete, same scale, much more complete. So you can see over a number of different cycles, we're not building up anything like the same amount of non-recoverable strain, or what we call non-recoverable compliance, in a polymer modified bitumen as we are with a paving grade bitumen. And the lower the non-recoverable compliance we have, the better the performance will be out in service. I'll now touch on low temperature rheological tests. For this, we use our bending beam rheometer. We take a beam of bitumen, we place it into a controlled temperature bath on 2 supports, and then we apply a load to it and we measure deformation, and from that we calculate a stiffness value. And there are 2 things that we tend to take away typically from that. Firstly is what we call the critical stiffness, and that's the temperature at which the binder achieves a stiffness of 300 megapascals, and what's called the M value. The M value is a measure of the rate of change of stiffness with time, and we also report the temperature at which the M value is 0.3. We can calculate another parameter from that which is delta TC. That is the difference between the critical stiffness temperature and the temperature at which the M value equals 0.3. Let's have a look at some outputs from that. Here you can see this is our critical stiffness at 300 megapascals. On this side, here's our M value equals 0.3. look at paving grade bitumen, we might achieve a critical stiffness at about -17. With different polymer modified bitumens, we can move that critical stiffness down to below -25, in some cases below -30. That's important because we can understand here that we would have to get our bitumen below, in this case, -27 degrees before we were in danger of it cracking. Similar thing for the M value. A paving grade bitumen reaches it here at about -17. Different polymer modified grades can take that M value down to below -20, below and below -30. That is really what I wanted to do as an introduction to bitumen and rheology. If we wanted to cover all of those different rheological tests, we would be here for really quite a long time. So what I tried to do is to get over to you, or to explain to you, the different rheological concepts, terminologies, give an introduction to different rheological test methods and why they're so useful, and then a highish level view of what we can do with calculation and analysis from those individual rheological parameters that we measure. If you want more information, do please go and have a look on our website. We have a range of technical information sheets covering all our major test methods, both conventional and rheological. They're available in a range of different languages, and they cover really the most important practical points that you would need to understand if you are about to carry out rheological testing. We're also some technical position statements, and we do have our data collection reports as well. Equally, we are here for you. We are a team that is here to answer questions. These are the contact people that to speak to. For technical information, it's myself. For health and safety information, it is Anja Sørensen. For sustainability information, it's Brice de Laporte. And for anything else on membership and the way that the association works, it's Siobhan McKelvey that you heard at the beginning. And that was an introduction to rheology.